we're going to be looking at implicit differentiation and its applications to finding the tangent line and normal line to 2D curves. We looked at a bit of this before the holiday in that Thursday lecture, where we have some 2D curve like this, okay, given as some function of x and y. For example, we can have x squared plus y squared equals xy, for example. This will give us some curve in 2D space. And what we want is at some point, let's say P, we want to find the equation for the tangent line and the line perpendicular to the tangent line, also called the normal line. So here we have the tangent line, and perpendicular to that, we have the normal line. Okay, and in order to find the tangent line and the normal line, we need to find the gradient at that point. In other words, we need to find y prime. Now, so far, we've been looking at explicit equations for y. So explicitly, we have y equals f of x. So that's what we've looked at so far. Now, to find y prime in this case, we just do d by dx on both sides. We have y equals d by dx of f of x. So y prime equals f prime of x. Again, we looked at all the rules of derivatives to evaluate that right-hand side. Now, for implicit differentiation, this is a bit different. So for implicit differentiation, in this case, we don't have explicitly y as a function of x. We have something like x squared plus y squared equals 1. Now, just given this equation, it's not clear what is a function of what. So we could have x and y being two independent variables. We could have x as a function of y. We could have y as a function of x. It's not clear what we have here. However, it's implied that this y is in fact a function of x. So it's implied that this y is actually y of x. But we don't write it out fully as y of x. We just write it as y, but we know that it means y of x. So if we were to write this out fully, which we're not going to be doing for the examples, it will be x squared plus y of x squared equals 1. So here we have explicitly written the y as a function of x. Okay, but it won't be written like this. It will be written like this over here. Okay, where we've got x squared plus y squared equals 1, and we know that y is secretly y of x. Now, the goal is the same. We want to find y prime. So we do the derivative on both sides, exactly like what we did in this previous case, where y was a function of x. So taking d by dx on both sides, we have d by dx of x squared plus y of x squared equals d by dx of 1. Now let's do the derivative. So d by dx of x squared, that will be 2x plus, now d by dx of y of x squared. We need to use the chain rule here. We have y of x as our inside function, and then something squared as the outside function. So we need to use the chain rule. So first the 2 comes down, so it will be 2 y of x to the 1 times, and then the chain rule says we need to take the derivative of the inside function, so that's y prime of x. And then on the right hand side, the derivative of a constant, that's going to be 0. Now I'm not going to write y of x anymore. We can just write it as 2x plus 2y y prime is equal to 0. We can cancel the 2's. So x plus y prime is equal to 0. And remember, we're still looking for y prime. So y prime is equal to minus x. Y prime is minus x over y. So given some point P being x and y, we can substitute x, we can substitute y, and that will give us the gradient or y prime at that point. Okay, so let's have a look at a few more examples, just finding y prime, and then we'll go on to the application of finding the tangent and normal lines. Okay, so let's call this example 1, and let's have a look at example 2. So example 2, we have sine of xy is equal to 3x squared plus y. So again, we've got this y inside some other function mixed up with x, so we can't directly write y equals some function of x. Okay, it's a bit more complicated than that. But we still want y prime, so we're going to take the derivative on both sides. So we're going to have d by dx sine of xy equals d by dx of 3x squared plus y. Okay, same as we did before. Now we've got the derivative of sine, and sine has some inside function there, x times y. So we're going to have to use the chain rule on that. And also on the inside, we have a product of x and y, so we're going to have to use the product rule on this inside part. The right hand side is a bit more easy, so the derivative of 3x squared, that's just 6x, and the derivative of y, that's y prime. So that's easy enough. Okay, so the derivative of sine, that's going to be cosine, so we have cos xy times, just by the chain rule, the derivative of the inside, and that's going to need the product rule. So we take the derivative of the x, that's going to be a 1, we leave y alone, plus we leave the x alone, and then take the derivative of y, that's y prime. Yeah. And then on the other side, like we said before, 3x squared, that will be 6x, and y, that will become y prime. Now, remember what the goal is? The goal is to solve for y prime. So we have a y prime over there, and a y prime over there. Okay, we want to solve for y prime. So let's expand out the left-hand side. So we're going to have y cos of xy plus xy prime cos of xy is equal to 6x plus y prime. And again, the goal is to solve for this y prime. So let's take all of the terms with y prime to one side, the left-hand side. Let's take everything else to the right-hand side, and then we can solve for y prime. So on this side, we're going to keep the xy prime. And then we're going to take over the y prime from the other side. And then on this side, we're going to keep the 6x and then take over the y cos xy. Okay. And again, the goal is to solve for y prime. So let's factor that out. So we're going to have y prime, x cos xy minus 1, that's left over. This is equal to 6x minus y cos xy. Okay, and again, we want this y prime by itself, so let's divide through by that other term. So we're going to have y prime is equal to 6x minus y cos xy, all divided by x cos xy minus 1. Okay, and again, given some point P at some xy, we can substitute x, we can substitute y, and that will give us y prime, which is also the gradient of the tangent line at that point. Okay, so let's have a look at the application to finding the tangent line. Okay, so in this first example, we have a 2D curve given here. X squared plus y squared equals x cubed plus y. Again, we can't write this as y equals some function of x. Okay, this curve is not even a function of x by the vertical line test, so we can't do that. Okay, but we want to find the tangent line and the normal line at the point 1, 0. So that's over here at the x-intercept. Okay, so let's start with the curve. X squared plus y squared. Okay, equals, and then we have x cubed plus y. Okay, so to find the tangent line, we first need to find the gradient. So that means we need to find y prime. So let's do the derivative on both sides. So d by dx of x squared plus y squared equals d by dx of x cubed plus y. Okay, now we can do the derivative. The derivative of x squared is 2x. The derivative of y squared, here we need to use the chain rule because this is y of x as a function squared. So we take the 2 down and we get 2y. Then the derivative of the inside function is the derivative of y, which is just y prime. And then on the other side, the derivative of x cubed, that's 3x squared, and the derivative of y, that is y prime. Okay. Now, what we want is to find the gradient at 1, 0. So always keep that in mind. So we want to find m at 1, 0. So x is 1, y is 0. So we could actually substitute that now. So if x is 1, that will be 2 times 1. Y is 0, so that's 2 times 0. And y prime, that will just be our gradient, m. Then it will be 3 times 1 squared. And again, our gradient is m. Okay, this term goes away. So we have 2 equals 3 minus m. 2 minus 3 plus 2 minus 3, that's minus 1, is m. So the gradient is minus 1. That makes sense. If we look back to the picture here, it's a downward slope, so we should expect a negative gradient. But we don't want just the gradient, we want the actual tangent line. So y minus y1 equals mx minus x1. We know m and x1, y1. We can use this point here, 1, 0. So y minus 0 equals m, that was minus 1, and x minus 1. So y equals minus x plus 1. So that's going to be our tangent line. Okay, now what about the normal line? Remember, the normal line is perpendicular to the tangent line. So if the tangent line has a gradient of minus 1, then the normal line will have a gradient of 1, because the product of the gradients must be minus 1. So for the normal line, we have y minus y1 equals m, that was going to be 1, x minus x1. And they intersect at the same point, so we can substitute 1, 0. So y minus 0 is x minus 1, so y equals x minus 1. Okay, and we can fill those in the picture here. So at this point, we can sketch in the tangent line, will be something like that, and then the normal line will be something like that. Okay, so we've got the tangent line, and perpendicular to that we have the normal line. At this point, 1, 0. Okay, let's have a look at the next example. Okay, so here we have an even more complicated curve. This can definitely not be written as y equals a function of x. Okay, but we still would like to find the tangent line and normal line at pi 0. So that's going to be at this point over there. Yeah, so as before, we start off with the equation for the curve. Sine x equals y cos y. Okay, so that's the equation for this curve. We want to find the tangent line, so we need to find the gradient, so we need to find y prime. So let's take d by dx on both sides. So d by dx of sine x equals d by dx of y cos y. Now on the left-hand side, that's easy enough to do. On the right-hand side, we've got a product of two functions. And also, y is a function of x, so we have cos of y of x, so we're going to have to use the chain rule there. Okay, so the derivative of sine x, that's going to be cos x, equals, we're going to take the derivative of the first term, so that's y prime, leave the second one alone, cos y, plus, now we leave the first term alone, so y, and then the derivative of the second, the derivative of cos, that's going to be minus sine, And then the derivative of y, that's y prime. So here we have cos x is equal to y prime cos y minus y prime sine y. Okay. So let's substitute what's given here. So we want this at the point pi 0. So x, that's going to be pi, and y, that is going to be 0. So we're going to have cos of pi is equal to y prime, that's our gradient m that we want. Cos of y, that's going to be cos of 0, minus y, that's 0, y prime, that's m that we want, and sine of y, that's sine of 0. Okay, now that's going to go away. That's all 0. Cos of pi, that's going to be minus 1. Then we have m, and cos of 0, that's just 1. So m equals minus 1 in this case. So we've got the gradient. We can find the tangent line. So y equals, y minus y1 equals mx minus x1. And we're interested in the point pi 0 still. So y minus 0 is equal to m, that's going to be minus 1, x minus x1, that will be pi. So y is equal to minus x plus pi. Okay, so that is our tangent line. Okay, what about the normal line? Again, the product of the tangent gradient and the normal gradient, that must be minus 1. So in this case, the normal line will have gradient 1, so that the product is minus 1. So we're going to have y minus y1 equals mx minus x1. Okay, the point is the same because the tangent line and the normal line intersect at the same point. So we're going to have y minus 0 is equal to m. We said that was 1, x minus pi. So y equals x minus pi. And we can also sketch this on our graph here. So the tangent line, that will be following the curve like that. And then the normal line, that will be perpendicular like this. So we have our tangent and our normal. Yeah, at the point pi 0. Okay, let's have a look at the next example. So here we have an ellipse sort of shape, but rotated a bit. And we want to find the tangent line and normal line at this point 2/3 and 4/3. Okay, so 2/3, 4/3, that will be somewhere around there. Okay, so let's start again with the equation for the curve and then d by dx on both sides. So we're going to have xy equals x squared plus y squared minus y. So we've got the equation for the curve. Okay, again, something like this, we can't write as y equals f of x. Okay? It's not a function. But we still would like to find the gradient and therefore find the tangent line and normal line. So d by dx on both sides. D by dx of xy equals d by dx of x squared plus y squared minus y. D by dx of xy, we need to use the product rule. So the derivative of the first term, that will be 1, and we leave the y alone. Plus, we leave the x alone, and then the derivative of y, that's y prime. Then on the right-hand side, the derivative of x squared, that's 2x. The derivative of y squared, we need to use the chain rule. So the 2 comes down to get 2y. Then the derivative of the inside function, that's the derivative of y, that's y prime. Then the derivative of y, that's just y prime. Okay, so now we can either just solve for y prime and then substitute the point, or we can substitute the point now and then solve for y prime later. So let's solve for y prime first and then substitute the point. So here we want y prime there, and there, and there. We want all of that together on one side. So we're going to have x y prime minus 2y y prime, taking that over, plus y prime, taking that one over, is equal to 2x, and then minus y, taking that one over. Here on the left, we can factor out the y prime, so y prime, x minus 2y, and then the 1 left over. And on the other side, 2x minus y. Okay, so we have y prime is equal to 2x minus y over x minus 2y plus 1. Okay, so now we can substitute the point. So that will be x is 2/3 and y is 4/3. Okay, let's see what we get substituting this. So y prime, that's going to be our gradient m that we're interested in. 2 times x, that will be 2 times 2/3, minus y, that will be 4/3, over x, that will be 2/3, minus 2 times y, that will be 2 times 4/3, plus 1. Now on the top, we're going to have 4/3 minus 4/3, that will be 0. Okay, so we have a gradient of 0. So what does that mean? Well, a tangent line with gradient 0 is just a horizontal line. So a tangent line with gradient 0, so m equals 0, is a horizontal line. So the equation for that horizontal line, that's just going to be y equals, and then whatever point we had here, so 4/3. Right, so here we just did the y minus y1 equals mx minus x1, but since m is 0, we just have y equals y1. And we can sketch this as well. So the tangent line y equals 4/3, that's just going to be this line over here. Okay, so that's our tangent line. And then the normal line, that's going to be this line here. And we see that the normal line is just a vertical line. So that will have a x value. So normal line, that will be x equals 2/3. Okay, so the horizontal tangent line, that is a y equals 4/3. And then the vertical normal line, that will be x equals 2/3. And we can fill both of those in here. Okay, so the vertical normal line, that will be at 2/3. And then the horizontal tangent line, that will be at 4/3. Okay, so remember, horizontal lines are possible. Okay, you can have a tangent line being horizontal, and we'll see a bit more of this later on when we look at turning points. So minima and maxima of a function, we'll see that at those points, the tangent lines are horizontal. Okay, but that will come later on. Okay, last example for today, we've got this curve over here. And again, you can't just write this as y equals f of x. Okay, it's more complicated than that. So we have e to the x times y equals e to the y plus x. And we want to find the tangent line and the normal line at minus 1, 0. So that's going to be over here. Okay, so let's start with the equation for the curve. E to the x times y. E to the x times y is equal to, and then on the other side we have e to the y plus x. Okay, so same as always, we want to find the derivative y prime. That gives us the gradient, and then from the gradient we can get the tangent line and normal line. So to get y prime, d by dx on both sides. So d by dx of e to the xy is equal to d by dx of e to the y plus x. Okay, for the first part here on the left-hand side, we've got e to the x times y. That's a product of functions, so a product rule. Derivative of the first term, the derivative of e to the x is e to the x, and we leave the second term alone. Plus, then we leave the first term alone, and then the derivative of y, that is y prime. Okay, this is equal to e to the y. Remember, that is e to the y of x, so we need to use the chain rule. The derivative of the outside function is the derivative of e to the y, so that's just e to the y, times the derivative of the inside function, that's the derivative of y, so that's y prime, plus, and then the derivative of x, that is just 1. Okay, so here we can either substitute the values and then solve for y prime, or we can solve for y prime and then substitute. Let's substitute first. So we're going to have x is equal to -1, y is equal